Hi everyone, welcome to another video on causal inference and machine learning. I posted a series of two videos on WML. Definitely go and watch that if you want to learn about W or device machine learning. I posted a series of three videos on do calculus and a structural causal model, Julia-Perl approach. And now I want to talk about potential outcome. And so this video is about potential outcome. Next video is going to about potential outcome and DAG, relating do calculus, or in a sense, a structural causal model, or directed acyclic graph to potential outcome. I'm trying to tell you that not only these two are not different, but they are exactly equivalent. You can, if you know one of them, you can get to the other one. And that's why it's very important to understand both of them or learn both of them. Because each one they can have their own pros and cons, but knowing both of them, not only you can actually relate different concepts together, but also you can actually attack problems differently. All right. So this video is about the potential outcome. So we have two causal inference, very popular causal inference framework. Um, Popular causal inference. All right. The first one of them is the structural causal model of Julia-Perl. This is what Perl. This is where the do calculus is, and this is where the DAG, directed acyclic value, is, and then the other one is potential outcome. By Donald Rowan. So this is developed by Donald Rowan. All right. So this video is about potential outcome. Now, let's actually have some definition here. Let yi and ti be the observed outcome and corresponding treatment for unit or individual I. Individual I. All right. Then potential outcome denoted for y subscript t, which shows what? Let me show you this copy. It shows the all possible outcome under different possibility of treatment. That's what potential outcome is. So it says that if I try different treatment, what are all the possible outcomes that I can under all different possible possibility of treatment? That's it. How do we show that? So let's say that if we have assume as an example for the binary treatment. Binary treatment. What does it mean? It means ti equal to 1 or ti equal to 0. So what is ti equal to 1? Receiving treatment. Not receiving treatment. For individual R, right? Remember, it's for individual R. So let's say we have n observations, n individual. T1 equal to 1, T2 equal to 1, T3 equal to 0, T4 equal to 1, T5 equal to 0. Like the last person did not really get the treatment. All right, so in that case, the potential outcome is defined as follows. Y subscript 0 and Y subscript 1 are. So potential outcome for individual I had he or she received the treatment. Had he or she received the treatment. A potential outcome or they did not receive the treatment. Did not receive the treatment. And this one is potential outcome for individual I, how he or she received the treatment. Do we have only these two conditions? Absolutely, because we have only two different possibilities of treatment. All right. So what is potential outcome? Potential outcome is the all different possibility of the outcome that you can have under different possibility of the treatment. That's all there is. Okay, great. Now, so what's optimize easy? What makes it a little bit more complicated? So what makes it, so the question that you may ask yourself is that, okay, I got this one. Then what's the difference between potential outcome and observable? Let's talk about this. Difference between PO and observed outcome. All right. So one thing you need to understand, and it's super important, is that potential outcome exists before even you start the experiment, before even you start the study. So what potential outcome says is that, hey, what possible outcome I can have, what possible response I can have to different possibility of treatment. Before we start the treatment, think about it. Before I start the treatment, I have some thought. Let's say medical doctor is thinking with himself that what should I do? Which treatment is the best? Okay, under this treatment, this is gonna be the outcome. Under that treatment, this is gonna be our outcome. Like, what are all the different possibilities that I can get after the surgery, after the study, after the experiment? So potential outcome exists before even the study starts. So I write it down. Potential outcome exists even before the experiment or study. That's super, super important. Then at some point, we decide to do a study. We decide to run the experiment, right? We give certain people treatment. Once we get these people treatment, we look at their outcome. That outcome is called observed outcome because we give them treatment and we look at the outcome. We actually observe the outcome, right? And that's the definition of observed outcome. Then let's first write it here. Then at some point, we decide to give some individuals a treatment. The outcome we measure for observed is called observed outcome. All right, great. Now, so it's up to now is clear. All right, so let me just make sure potential outcome here. Now, one thing that is very important here is that let's go back to this notation. Y subscript 0, Y subscript 1, and individual I, and YI. So this is PO for if unit I is treated, unit I is treated, individual I is treated. PO is not treated. Is not treated, and this is observable. Right? So we decided at some point to do the experiment, and we realized the unit I actually received the treatment. If the unit I receives the treatment, the outcome that we observe is called the observed outcome. In that case, for unit I that receive the treatment, y subscript 1 I is equal to yi. And that's the relationship between potential outcome and observed outcome. Okay? For those who receive the treatment, the potential outcome, had they received the treatment, is equal to the observed outcome. This is one of the most important things you need to realize. And then y0 of I is unobserved, missing. This is the most important thing I want to tell you. Hidden. In the language of causal inference, we call this one factual or observed. We call this one unobserved, missing, or hidden, or counterfactual. All right, super important. So, potential outcome for those individuals, had they received the treatment, is the same as the observed outcome if they actually receive the treatment. Okay, this is super important to consider that. So I can write it down here just to make sure you have it. Potential outcome for unit I, he or she received the treatment is equal to observed outcome if unit I actually received it. Super important. The most important thing you need to know. That's the whole idea of a potential outcome, counterfactual, and factual. All right. Now, since this is actually very important, we have actually equation that actually map these two potential outcome for the case of binary, of course, to the observed outcome. And this is called consistency equation. Consistency equation. What does consistency equation says? So consistency equation is a way to relate the observed outcome to the potential outcome. I write it down. It's equation to relate observed outcome to potential outcome. What does it say? It says y I observed outcome for unit I is equal to 1 minus ti times y subscript 0 of I plus ti y subscript 1 of I. Let's see what it says. Let's see what it says. If the observed outcome for unit I is equal to 1 minus ti, so that's a treatment for unit I, times potential outcome when this person is not treated, plus ti, the treatment for the unit I, times the potential outcome if this person is treated. Let's take a look at this. If this person is not treated, means what? Ti is equal to 0. What's going to happen? If ti is equal to 0, the observed outcome is equal to 1 minus 0 times y0 of I plus 0 times y1 of I. So it's equal to this. Y of I is equal to y subscript. And if ti is equal to 1, then if this person receives the treatment, we get yi is equal to 0 times and this becomes this. There you go. And that's what we discussed about. This is called consistency equation. Great. Now let's talk about average causal effect. So based on this discussion that we have, it's very important to note something, guys, that let's consider a unit I, right? For any individual I, you either get the treatment or you don't get the treatment, right? So I either get to see your outcome under you receive the treatment or the outcome under you don't receive the treatment, not both. In majority of the experiment, that's the case, right? So always one of them is hidden, one of them is observed. And it's very important to consider this. Why? Because in causal inference, we do always the sum to calculate some quantities here. So we have something called individual treatment effect. Treatment effect. So what does it mean, individual treatment effect? You can write it as IT. It's the potential outcome if you receive the treatment minus potential outcome if you didn't receive the treatment. So that's the definition of it. So what's the answer to this? Let's say for unit I want to see what happened if you receive a treatment minus what happened if you didn't receive a treatment. Well, I run an experiment, I give you treatment. I have the observed outcome for that, but I don't know the observed outcome if you didn't get the treatment. Or if you didn't get the treatment, I don't have observed outcome if you get the treatment. So always one of them is missing. Always one of these quantities is missing. So this one is undefined. Since always one of them is missing, this is undefined. Or we can write unobserved. We don't know that. Okay? It's very important. Since this is the case, we cannot define the average causal effect. We cannot define the individual causal effect. And this is not a valid or defined quantity. Therefore, we need to use a population-based outcome. We need to use a population because in an individual level, this is not going to work. Therefore, we have another terminology called average treatment effect. And this is the most popular terminology that you see in causal inference. It's called ATE. Some people call it LIF, average causal effect. An average causal effect, average treatment effect, is equal to what? Sum of I from 1 to n minus I from 1 to n divided by n. You know what? I want to calculate the average. So here we assume everyone has an equal opportunity, one over, like the normal average, right? The uniform average. So why is this defined then? Okay, so let me see how I want to do this. I want to make sure that everyone is on board with this. So we have a couple of units here. I have an I here. I have 1, 2, 3, 4, 5, 6. Okay, good. And for each one, I should have the TI, whether I get the treatment or not. 0, 0, 1, 1, 0, 1. And then I have Y subscript 0, I, Y subscript 1, I, and then YI, the observer. Let's take a look at this. For unit I, if they didn't get the treatment, let's say the outcome, you did not get treated. Let's say the outcome is binary. You get 0, here you get 1, we don't know. Because you get the treatment, I don't know this one. We don't know. Here, let's say you get 0, and here we don't know. For the Y1 potential outcome, if you get treated, we don't know. We don't know. Let's say 1, let's say 0, we don't know. Let's say 1. All right, so the observed outcome is very simple. If you didn't get the treatment, the observed outcome is the potential outcome under you did not get treated. So 0 for this case is 0. For this case is 1. Is equal to potential outcome if you get treated. For this case is 0. And for this case is 0 as well. And for this case is 1. Okay. Very important to know actually this. Okay. Now, if you calculate the individual outcome, what you're gonna do every time you're going to calculate this one, subtract this 3. So you see that at each point, for each row, this value is undefined, just for each individual. If you calculate the average, what's going to happen here is that. So we're going to say sum of I from 1 to n, this is for 1, for potential outcome undertreated. What's going to happen? I have 1 plus 0, this one, I'm adding this one, and this one, plus 1, minus. Sum of for the 0 one, I'm adding this one, and this one. 0 plus 1 plus 0. And then I divide it by 6. So the answer is going to be 1 over 6. It's the point. Because you're talking about the average. All right? Fantastic. So it's called average treatment effect. And that's why we use actually this terminology. This is for the population base. So usually also if you want the consistency equation, you can also relate it to here. Observed outcome is equal to 1 minus treatment times potential outcome under no treated plus treatment times potential outcome under treatment. This is also consistency equation for the population. All right, fantastic. Now, I want to tell you something else as well. It's called the average treatment effect among the treated, or the average treatment effect among untreated. I think it's important to know that because you use it all. Average treatment effect among treated and untreated. Okay. As the name suggests, it says that, you know what, instead of calculating the average treatment effect for all the individuals, why don't you go ahead and calculate the average treatment effect only for those people that got treated, among those people that actually received the treatment. Okay, so what's the average treatment effect for treated? ATT. So here in the language of the causal inference, this ATE, we also show it like this. The language of mathematics, like through the expectation as well. So here, for the ATT, what does it mean? It means that expected value of potential outcome for treated for those that actually receive the treatment minus potential outcome for people that did not get the treatment for those among those that did not. Sorry, for those people that receive the treatment. But remember, potential outcome exists before the treatment starts. Before treatment starts, potential outcome. We get to the identifiable condition, and you'll see actually why they are actually even meaningful. So this is the average treatment effect for those among the people that are treated. And then average treatment effect for untreated is the expected value of potential outcome had you received the treatment among those that did not receive the treatment minus. I have a very nice analogy related this one from potential outcome to that. You learn this one very, very well. You see that this language is easier than that actually. Y 0 given t equal to 0. So that's the average treatment effect for the people that are untreated. And this is for the treatment. This is also very important terminology to remember in causal inference. This is one of the metrics that people also calculate. All right. So that's it for the video on the potential outcome. I think I covered everything I want to tell you about potential outcome. In the next video, I'm going to talk about potential outcome and that, and how to relate them together. So you will have tools to actually every tool that you need to know in the causal inference to attack any problem. And also I talk about the identifiability condition. And then try to explain in terms of that, also in terms of potential outcome. Like always, if you like this video, please like, subscribe to the channel, and share it with your friends. And I'm looking forward to read your comments if you have any questions. Thank you so much, and see you all in the next video.